Okay, so as recap, yesterday we started the graphs, or we were looking into how to identify groups or clusters in networked data. So we were discussing that in case of data sets like protein interaction or Facebook friendships, the data sets are not the discrete data points. They are not only represented by their individual feature vectors, but also by the other connections among them. Okay, and then in the connected structure, how can we identify that which groups of nodes are closer to each other than they are to the other sets of nodes. So basically, how can we identify clusters or groups in the network data? Then we discussed what is the graph. That is a set of nodes and a connection set of connections among them, which we call the edges. And we also discussed that the edges can be unweighted, so each edge has uh, the same weight, and it is not important that like so all the edges are equally important. And weighted graphs mean that different edges have different weights, and the examples are the email communication networks to denote importance about the communication channel between two people, or the city or road networks to maybe to denote distances. So when we do an optimization problem on them, say for to transport a particular item which will be my shortest path, I can use the edge weights to calculate that. Okay. So graph data shows relationship between objects pairs. So therefore the centroid, like we were using mean, mode, these are often not valid in the graph. Like the centroid mean the notion of centroid that we have used till now. So then what does centroid mean in the graph, and how can I define a center in the graph? How can I identify clusters in the graph? That we will see now. So first we will look into the unweighted graph. So the first algorithm for graph clustering is called the minimum cut or mean cut. So some of you may have taken graph theory in one of your BTech mathematics. There you may have also learned about the things like this spanning tree, mean cut, max flow. So this mean cut is the same. So basically, what we will try to identify that partition or nodes in two groups S1 and S2, so that the edges between S1 and S2 are minimized. So we will try to identify two subgraphs S1 and S2 containing say some nodes in the graph subgraph S1, some nodes in the subgraph S2, so that the edges between these two will be minimized. Let us take an example. Say if you can see in this graph, this A, B, E, F, they are closely connected, and C, D, G, H, they are closely connected. What do I mean by closely connected? As you can see that A is connected to E, F, B. B is connected to A, E, F. F is connected to A, E, B. So they are fully, so this part is a fully connected sub subgraph. So the one vertex the one vertex is connected to all the other three vertices. So the same thing is happening also in the subgraph, that CDGH. This part is also a fully connected subgraph. By fully connected, I mean the one vertex is connected to all other vertices. So there is a direct, like one distance connection from one vertex to another. But if you see in this part, this B, C, F, G, as you can see, B is connected to C, C is connected to G, G is connected to F, and F is connected to B. So so this part, if we cut, we will just lose two connections. But if we cut between this part, there we will lose the multiple connections. So the mean cut partition will be A, B, E, F and C, D, G, F. because the edges between, say, this is the set S1 and this is the set S2, this is minimized. So how do we do graph clustering using mean cut? So we use a mean cut algorithm to break a graph into two sets. So now understand one thing. We are using the minimum cut approach to do graph clustering. We are not learning minimum cut here. So there is an algorithm to understand actually in graph theory that how to identify the mean cut in a graph. We are using that approach to identify how can I divide graphs in a two set of subgraphs. Okay, and we are doing graph clustering in this way. So use the mean cut algorithm to break a graph into two sets. Use the mean cut algorithm to further. So just let me take one. So how do we do clustering? Say if you have a group of people and I say that you need to break them into different groups. So how will you start? First, generally what we do is that first we divide the two groups of people, say, in the two sets based on some characteristics. Then within each of the set we again divide them into another two sets, okay, based on some characteristics. And then like, and we repeat this process until, say, we have something like each group should have 4%. So until we reach 4%, we repeat the process for each of these group, breaking down into two subgroups and going on like this. So we also use the similar technique here. We use the mean cut algorithm to kind of, cut a graph into two subgraphs, and then again we use the mean cut algorithm on each of the subgraphs to cut them into smaller graphs until the stopping condition is reached, which can be the minimum size, or it may be that there is no further minimum cut in the graph. Okay. If you are interested to know mean cut algorithm, I can point it to you. So I will put up the link. You can go through that. It is very easy actually. So we will now look into one of the mean cut algorithm, that how mean cut works. That it is called the Kruger's mean cut algorithm. So it is based on the age contraction. So what does age contractions mean? That we will repeat this algorithm until just two nodes remain. So in each of the groups until two nodes remain, we will keep on cutting down the graph. So how will we start? We will pick an edge at random and collapse.
और ये MLF भी पढ़ना पड़ेगा.
हो गया discussion. Thank you. Please keep your microphones on mute. So we will pick an edge at random and collapse its two endpoints into a single node. So let us see how will you do it. So let us take our first example graph. So we have a total 14 edges, and we will choose the edge B to F with probability 1 by 14. Why 1 by 14? Because this is an undirected graph. So if I have 14 edges, so all the edges are equally likely. So picking any of the edge is also equally likely. So now say I just pick one of the edge B to F with 1 by 14. So now if I take out this edge, what happens? This edge is kind of, think that you have a string, and at the edge of the string there are two balls. So you pull out the string. So what will happen? These two balls will collapse on each other, right? So the same thing is happening in this algorithm. Like we are thinking like this, that if I take out the edge, so B and F will be collapsed into a single node, which I now call the node BF. Okay. So now we have 13 edges, one is the one edge length. So again I pick G by H with a probability of 1 by 13, because again this is an undirected graph and all the edges are equally likely. So now if I pick GH, what will happen? My GH will G and H, two different distinct nodes will collapse to the one single point, that is GH. So now from 12 edge, I pick randomly the node DGH. So with probability, what? 2 by 12. Now why it is 2 by 12? See, because there are two edges now. Why there is two edges? Because I have collapsed GH, this edge is gone, but my G was connected to D and H was also connected to D. So this become a double connection. Like this, my G was connected to C and H was connected to C. So again, this became a double connection. The same happened when I collapsed this edge BF and the A to BF, there are two edges, and E to BF, there are two edges. So if there are 12 equally likely edges, and this represent two edges, so the probability becomes 2 by 12, right? So simple probability rule. So again it will collapse and it will become DGH, and there will be three connections between C and DGH. So now I have 10 equally likely edges. Say my system randomly chose edge AE with a probability 1 by 10. So it became AE and four edges to BF. And now I have 9 edges. I randomly chose this edge with a probability 4 by 9. And my graph become like this. And I have 5 edges now. Say I now choose this one with a probability 3 by 5. So this is my graph. So now I have just two nodes. So what was my stopping condition? That I will repeat the condition until the two nodes remain. And now I have only two sets of nodes. So basically these two represent my two partitions in the graph. So in this way, I cluster a graph into two sets of subgraphs. And as you can see, this.
Ma'am, why are we choosing in this sequence only?
We are not choosing in this sequence. We could have chosen in some other sequence also. We are picking an edge at random. So that's why this probability are coming. So this is one particular sequence example that is shown. You can do it with any other sequence of shapes. So the idea is that you will come to this like this. Say, I will tell you, in this, why are we choosing this one 4 by 9? Because this has a higher probability. Say, even if you are choosing at random, so because this has a higher probability, we are assuming that this will be chosen first. So in this case, this has the highest probability. So that's why we are choosing it, because the more probabilities, the more likely it is to get picked up in the random. But for these ones, you can start with any edge and you will come down to this. So you can try it at your room or at your own time. Okay. So we are just picking randomly. And
so ma'am, if we are picking of the highest probability, then we are guaranteed to achieve at this type of clusters. Is it right?
Actually, in this algorithm, you are guaranteed to come up with these types of clusters. So the algorithm gives you mean cut. So that's why it is the mean cut algorithm. But why we are choosing the highest probability in these steps? Because see, when we are picking at random, so if these edges have high probability, so their chances of getting picked will be more. Okay, so that's why.
Okay, ma'am.
Yes.
I'm in the left side, the last diagram.
Yes.
Ma'am,
Yes.
if we are going by higher probability, we should choose that C to DGH.
Yeah, we can choose the C to DGH. See, The point is that the algorithm goes with pick an edge at random. So the random means we can pick a lesser weighted edge, like a random edge, or this case we are randomly choosing the high probability edge. Okay, we could have chosen this edge also, like CDGH. Then at first we would have this AEBF and CDGH. Then at the next step we would have collapsed it. So we would have come from to this through a different path.
Ma'am, then can we ensure that always the final answer will be ABF and EDGH? Like it could have been different form of clusters, maybe.
I think that we can ensure, because in mean card, that is the whole point. Otherwise, it won't be a mean card algorithm, right? We can ensure that we will always have the mean cut clusters.
Ma'am, if we are choosing randomly and we choose C and BF in the third last choice, then the cluster will be different.
This one, right?
Yes, ma'am.
Just a second. Yes, but actually, see, in this case, so actually, somewhere we have to consider the probability too. Okay, I understand the question that if we choose randomly, it will become C to BF, and that's why we are actually considering this the probability at this stage. So, uh, okay, so just let me come up with better resources to answer your question. Okay. I will I will point to some resources. I will give them in the course teams. Hmm. Oh, okay.
Okay, ma'am.
Okay, so and also with mean cut, we assign a value that of the what is the mean cut value means between the two graph sets that we have come up with, or the two partitions, what are the number of the edges. So in this case, the mean cut value was 2. Like there are 2 connecting edges to the remaining. Okay. And I think actually if you also collapse C to B, then after a stage you need to you will need to group them into different subsets. Let me just work it out after some time. Okay, so I think the answer is here. So as it is a randomized algorithm, because yes, we were picking the nodes at random. So we will run the algorithm multiple times. So it will produce multiple cards. So very rightly, as you have pointed, and then we will take the card with the minimum value. So basically, if we are not considering the probability, just any random value, then at the end, like running it after multiple times, we need to take the one with the multiple value, sorry, with the minimum value, which actually we are coming up with the probability, the edge connection probability. Okay.
Ma'am, so the probability is of no use in the algorithm.
Actually, see, as someone pointed out rightly, that if we do not take this 4/9, 4/9, then we could have collapsed this age, CBF. Okay, and another person also said that is the main cut always for the ensured. So now the thing is that as this is a randomized the algorithm, we could have very well collapsed it like CBF. Then we would have a different bin cut value than this. Like say like we would have 3 or 4. Now the idea is that say in this graph I can see, but when the graph becomes very large, I do not know whether the mean cut value is like 10 or it is 15 or it is 100, right? So now for that cases, what do we do that if it is a truly randomized algorithm, we run it multiple times. So if we run multiple iteration and even if it peaks randomly, but the probability that the minimum value from the multiple outputs will very closely represent the actual mean cut in the graph. So we take that. But as this is the small graph, and in this example, we are using this to like manually just to show, we have used these probability values to denote that how we can quickly come to the mean cut too, because we can also see with our like just by naked eye that the mean cut value is 2. Okay. So actually, when you implement the graph, what happens? You are picking it randomly. So the like you are assigning a random probability to each node to get picked up. Did I answer your question?
Yes, ma'am.
So yeah, so that's why in the implementation, like especially for very large graphs, because if we are talking about like the Facebook friendship graph or this protein interaction graphs, uh, there are millions of nodes, right? So that's why we run it multiple times so that I can have multiple outputs and I can choose the minimum value from them because it is a randomized algorithm. So, okay, so I think did I also answer the previous questions?
Yes, ma'am, it is clear now.
Yes, ma'am.
Okay. Okay, now let us move on to the clustering the weighted graphs. So for weighted graph clustering algorithm, we will use a method called hierarchical clustering. So the hierarchical clustering can be of two types, agglomerative or divisive. Acha, can actually I need to take a 5 minutes break. I have someone at my door, so very sorry for the interruption. So uh, with your permission, I am turning the screen off for 5 minutes, okay? If it is okay. Okay, hi everyone. I am back and very sorry for the interruption. So can you see my screen?
Yes, ma'am.
So there are two types of hierarchical graph clustering. As the name suggests, hierarchical. That means we go either from bottom to up or top to bottom, like a hierarchy. So if we go from bottom up, that is called the agglomerative clustering. So what happens that we start with each node. So we consider each node a single cluster on itself. And as the name suggests, we gradually merge say like two nodes and we go up. We merge two nodes, make one of the clusters and we go up. So just like so that is why it is called the agglomerative, because we are kind of making like we are kind of grouping from bottom to up in the nodes into different clusters or different subsets. So just like in the previous example, we saw that we are collapsing the edge to bring two nodes and like fusing and naming the nodes like AF, sorry, AE or BF. So in this way, in this thing also similarly, we are taking two nodes and we are putting them in a cluster, and then we are considering the cluster as a single node. So this is the bottom up approach because it starts with the node. Another is other divisive approach or the top down clustering. So in this clustering, we consider all the nodes to be in the same cluster, and then at each step we partition the cluster so that the different two sets of the cluster have the maximum distance. Why the maximum distance? Because when we are divisioning a cluster, so we need to ensure that the two parts of the clusters or the two subclusters are as distinct from each other as possible. So that means in the graph term, they are as distant from each other as possible. So then only we will get good partitions, right? Because if two partitions are very close to each other or overlapping with each other, um, uh, then my clustering, the output will not be very good, right? So there are that's how we go. We do hierarchical clustering. So mainly, the most commonly used technique is the agglomerating clustering, or which is called the hack. Okay. And so there are some important points. So why we do this? Because it does not require the number of clusters in advance. So we do not need to know that how many clusters at the end we will have. As we go on grouping the different nodes in clusters, we find that uh, uh, we also determine the number of the clusters, and for that's why we also need a termination or a readout condition, that when do I stop clustering. So it can be a distance threshold, because again the requirement is that two clusters are as distant from each other as possible. So we will go through the hack process or hierarchical agglomerative clusterings, and it is, as I said, very widely used, and it is simpler also to do. We just go from bottom to up, keep going up with clustering the nodes too. So let us see the example. So first of all, how do I start clustering? So say this is my starting point. So each nodes of the graph are represented as individual cluster. At first, we consider that each of the nodes are individual clusters. Just so now we need to, but if I need to group the nodes into different clusters, I also need to determine a similarity function to come up with the similarity of these two instances. Otherwise, how will I know that which two nodes I should group into the one cluster? And as you can see in this process, it is always I am grouping two nodes to one cluster. Say these two I have first grouped into one cluster, and now say this point it represents one of my clustered nodes, and then this and this I have grouped into it another cluster. So it is always two nodes at a time. So I just need to identify two instances which are similar to each other to group them in a cluster. So start with all instances in a separate cluster, then repeatedly join the two clusters. Those are most similar. The history of merging forms a hierarchy, and this diagram is also called a dendrogram. And this looks like a hierarchy, right? How we have merged the nodes. So say for example, in this case, just consider the spatial closeness of a node to each other. Also says the similarity between them. So what did we do? We took these two closely these two similar nodes and we group them in a cluster, and then this cluster and this node is also similar, so we group them into a second cluster. So in this way we got this cluster, and then gradually we group this one to a cluster, this and this node to a cluster, and then this cluster and this node to again a cluster, and then we add this node again to this cluster, and then finally the cluster that we got with these two nodes we form in these two. And then this is my end hierarchy, because this cluster and this cluster can be grouped to form the whole graph. So this looks like an steps from bottom to up, and this is called a dendrogram. And the advantage is that we can cut it. Say if we cut it here, how many clusters we will get? Two clusters. And if we cut it say at this point, how many clusters we will get? Three clusters. So we can decide how we can come up with the clusters. So the important question is, how do I define or determine the nearness of the cluster? The whole thing is based on the similarity between two sets of nodes or two sets of clusters, right? Okay. So now there are different ways. So in graph terms, the similarity can be defined in terms of their connection. So either so the first is the single link variant to determine the closest pair of the clusters, that is the distance of the closest points. The second is the complete link. That means if the graphs are completely connected, for connected graphs, we will take the distance of the farthest points, like which two points are very distant than each other. And the in between these two, we have the average link clusters. That means we compute the distance, the average distance between the pair of the elements. I think we have an example. Yes. So yes. So just but remember, single links means distance of the closest point. So let us see how single link is defined. Okay. So how do we define the maximum similarity of the pairs? So say for example, I have a cluster 1 and cluster 2. And in this cluster, say I have 2 nodes. In this cluster also I have 2 nodes. Now in the actual graph, these nodes may or may not be connected between them, right? So in this case, if these nodes are connected like this, as you can see, this is a weighted graph. So the nodes have the edge weights because we are now clustering the weighted graphs. So in this case, in this single link clustering, what did we say? We will take the closest pairs. So the similarity between the two clusters Ci and Cj is defined as the maximum of the similarity between x and y, where x belongs to cluster Ci and y belongs to cluster Cj. In other words, it means that if I have two clusters and a set of nodes in each of the clusters, then the maximum value or the maximum similarity between two nodes across the two clusters will be considered as the similarity between the two clusters. So basically we are taking the highest value. Okay. So distance between cluster, but just a second. I think there is some problem. Okay, I don't think it will be 2. The distance between cluster 1 and 2 will not be 3. Okay, because if we take the maximum value is 10. So I need to check. But as per the definition, the value is not 3. Actually, 3 is the minimum value, which will be okay. Sorry. I did the mistake. Yes. So why the distance between cluster 1 and 2 is called is 3, because it is so these edge weights in this case actually, so the minimum edge weight is representing the maximum similarity. So actually generally it is the other way round. So that's why I did the mistake. So basically, as the single link is defined as the distance of the closest point. So in this case, this 3 is actually a measure of the distance. So that's why these two nodes, like if they are the closest to each other, then they are having the maximum similarity. So just like we measure the distance between two data points, and the lesser the distance, the more similar they are. Okay. So sorry for the confusion. So if we see the single link example, say in a two-dimensional space, graphically, how how will it look like? As we can see that we will go by the closest examples and then grouping them into a cluster. So we'll start with considering each node in a single cluster. So now these two nodes are closest to each other, so we group them in a single cluster. These two we group them in a single cluster, and likewise these two also we group them in a single cluster. Then this cluster and this cluster represents, say now we can think that two distinct nodes. So again this cluster is closest to this cluster than this cluster, so we will group these two, and similarly it will happen for these two, and then at the end we can group this whole in a single cluster. Okay. So any question till now?
Ma'am, how do we calculate the distance between clusters?
You mean this one, this part? How do we know? These are the edge weight, the distances.
Distance between clusters.
Yes, so distance between clusters. So this is the formula for computing. So we are measuring the similarity between the clusters based on the nodes present in each clusters and how they are connected to each other. So see, we have say this picture, we have this representation. So basically what happens, these nodes in the original graph, they are somehow connected to both each other, right? If they are completely disconnected, then we do not need to do clustering, because if there is no connection, then we can right away divide them into two separate groups, correct? So now say after doing a round of clustering, we are at this point that my cluster the one contains these two nodes, say AB, and my cluster 2 contains these two nodes, CD. Then how can I come up with that? What is my similarity between these two clusters? And similarity means the measure of distance, right? The lower the distance, the more similar two instances will be, just like we have seen in our previous algorithms. So how do we measure the distance? The idea is that the node that these clusters have, for the single link approach, we will take the minimum distance, like uh, um, uh, the idea is that as we will take the distance measure between the closest node between the closest nodes across the two clusters. So that means we need to take the minimum distance between these two clusters, or these two nodes across the two clusters. So in this case the distance is 3, 6, 4, 10. So what is the minimum? 3. So that means these two pairs, say A and C, are having the maximum similarity between them. So the distance between the two clusters is 3. So if we have taken the complete link approach, then the distance would have become 10, because we will consider the farthest pair. Now, if your question is how do we know these 3, 6, 4, 10? So these are basically the graph edge weights. So when we are so as we are doing clustering on the weighted graphs, at least at the stage of clustering, we assume that we already have the graph with the nodes and the connection and the edge weights presented with us. So we are not here assigning the edge weights to the graph. We already have a weighted graphs, and based on the information on the weighted graphs, we are running our clustering algorithm. Am I clear?
Yes, ma'am.
Okay. Yeah. Yes. Please feel free to ask questions. If you are having any doubt, please. It may seem very trivial, but please don't hesitate. Okay, because maybe most of you are doing this for the first time, or at least some of you. So this kind of confusions are sorry, not confusions. My apologies. The questions is very likely. So now, what is the problem with the single link clustering? So if we have the chain or the elongated cluster, say like this, what is happening? See, these two things, this group and this group, or this cluster and this cluster, they are far away, but we are connecting them into single cluster. And the another problem is that when we come up with these two clusters, we are only considering these smaller red circles to group them in the cluster, right? So we are now, by the single link approach, how will we calculate the distance between these two sets of cluster, these two smaller red circle. Actually, it will be considered based on these two closest pairs, right? This one and this one. But as we are considering this, see this example and this example, these two are very far apart. But because we are taking the closest pair, they are coming in the same cluster. So for that, to kind of as a remedy to this problem, that if we have the elongated clusters like this or kind of like these chains, okay, we come up with the complete link approach. So what complete link approach says, we consider the similarity between the two clusters based on the farthest pairs of node across the two clusters. So now, how do I determine the similarity between two clusters Ci and Cj? It is the minimum of the similarities of x and y, where x belongs to cluster Ci and y belongs to cluster Cj. So the same example, cluster 1, cluster 2, the 4 edge weight 3, 6, 4, 10. But now in this case, the distance between cluster 1 and cluster 2 will be 10. Because now we are considering the farthest pair of nodes to be to represent the similarity between the two clusters. So is it clear till now?
Yes, ma'am.
So this approach makes tighter clusters, like more spherical clusters, which are typically preferable for different applications. So if you remember the protein interaction network application, protein interaction network graph diagram, then you would have noticed that almost all the clusters are kind of spherical in shape. So those kind of clusters are preferable for different applications. So now on the same diagram, if we do the complete link example, now how are we determining the cluster, the similarity between the two clusters based on the set of nodes which are farthest apart from each other. Okay, so these two will be again, so these are only these two, so I will come up with the same cluster. For the first step, I am coming up with the same set of clusters. Now what happened in the next step? If you recall, in the single node clustering, the clusters were formed like this horizontally, and in this case these are formed like vertical, like if we see the representation. The reason being, in the single link clustering, we were taking the among the clusters node, the minimum of the distances to be the similarity measure, but now we are taking the maximum of the distances. So now, just from the picture, if we take the maximum of the distance between two clusters, the distance is between this point, the distance is between this point and this point, right? And across these two clusters, the distance will be, say, between this point and this point. So now we can see actually this distance is lesser. So the similarity of these two clusters are more, so they are grouped like this. Okay. So the same sets of nodes, the two different output for clustering. If we use the single link clustering or the complete link clustering. So any question till this step? So any question? Okay. So now we will see a detailed example. Okay, so for that, first, how do we represent graph? Like we cannot feed a graph in the computer by drawing sets of nodes and the edges, right? So how do we represent graph mathematically? Anyone?
Ma'am, adjacency lists or adjacency matrices.
Yes, by using adjacency matrices. So this is actually the matrix representation of a graph or a network which have 5 vertices. So 1, 2, 3, 4, 5 and 1, 2, 3, 4, 5 in this side. So as we do not have any self connection, so all the diagonals are 0. And then this value to represent the edge weight between the node 1 and 2. And why this top right hub is empty? Because as we are learning on the undirected graphs, basically the value of the 1 and 2 will be the same as 2 and 1. So these graphs, like, it can be transposed along to across its diagonal. Okay, so that's why only these sets of values uh, are important, because the rest are the same about this. So here 9 represents the edge weight between the node 3 and the node 4, or the node 4 and the node node 4 and the node 2, and 3 and 4 is 7. Okay, because 4 and 4 is 0. So now let us start with single link clustering. So in single link clustering, we consider the closest pair of the clusters across the clusters, right? So let us first see what is the closest pair that is having the least distance is the nodes 1 and 2. So we connect the node 1 and 2. Next, how do I calculate the distance between this cluster 1, 2 and 3? So it will be minimum of distance between the 1 and 3 and 2 and 3, right? So that will be 3. Likewise, we will calculate all the pair of distances between the cluster the 1, 2, like if we say we take a node here. These nodes represent D12. So now we need to calculate the distance of this D12 with all the 3 nodes which we have considered a single cluster. Each a single cluster on its own. So how do I calculate the distance? So as this cluster has 2 nodes, so 1 and 2, and all these clusters have only 1 node. So the distance between D1 and 2 and 3 will be the distance between the minimum of the distance between D1 and 3 and D2 2 and 3, which from the matrix we can see the minimum of 6 and 3, which is 3. Then the distance between D1 and 2 and 4 will be D1 and 4 and D2 and 4, which will be 9. And D1 and 2 and 5 will be D1 and 5 and D2 and 5, which will be 8. So now again, which 2 clusters are mostly similar? This one, right? Because this has the least distance. So we will connect like this. Okay. So now my cluster become D1, 2, 3. Now I need to consider this node. So can you see it once, like just check that if you are able to understand this step, and ask me if you have any question. Okay, fine. Okay, I am going to the next slide. Okay, so now my cluster is D123. So now my matrix gets transformed like this. See, at the first stage, I had in my matrix all the nodes at the single entity, a single row and single column. So then when I first grouped the nodes 1 and 2 in the single cluster, so then these 2 nodes collapsed to a single entity to the 1, 2, and all the distances are updated accordingly. Now again, as I have connected this the 1, 2, 3 in the second cluster, so now my nodes are 1, 2, 3, and all the distances are updated accordingly. So now how I will calculate the distance between D1, 2, 3 and 4? It will be the minimum of D1, 2 and 4 and D3 and 4. See, it will not be minimum of D1 and 4, D2 and 4, because D1 to 3 is the clusters D1 to this one, D1 to and 3, right? The other reason being that we already have computed the distance like 1, 2 and 4 at the previous step. Okay, so now it is minimum of 9 and 7, that is 7. So how do we know it is 9? From this metric. Okay. Because this matrix is already updated for the minimum distance among between the 1, 4 and 2 and 4. If you see in this step, we have already calculated the minimum distance and we have updated the matrix. So that's why in this step actually we do not need to again calculate all the pair of distances like 1, 4 and 2, 4. Instead of that, we will take this the distance between the 1, 2 and 4, because we have calculated and already stored it. So both similarly between 1, 2, 3 and 5, the minimum distance will be 5. So now which one is having the minimum distance among the cluster 1, 2, 3 and 5? This one, right? So how will okay, so actually 7 and 5, but there is another thing. When we are doing the clustering, it is not just that we go from the 1 to 3 and then what will happen, then how will we add 1 to new node to the cluster 1, 2, 3. We also need to check that, say, between 4, 5, so these two nodes, will they be grouped in a cluster? So see, the distance between the 1, 2, 3 and 4 is 7. The distance between the 1, 2, 3 and 5 is 5, and the distance between 4 and 5 is 4. So for the clusters, the 1, 2, 3, 4 and 5, the closest pairs of clusters are 4 and 5, right? So that's why we have joined these clusters 4 and 5. And then at the end, we have this D1, 2, 3 and D4, 5, and their minimum distance is 5, and we have joined them. So we would have anyway joined them. Okay. So any question till now?
Ma'am, I have a small doubt.
Yes.
Here, can't we make 1 and 3 as cluster? Should it be always consecutive?
No, we cannot make 1 and 3 and cluster, because see, in the first step, what is the distance between both 1 and 2? It is 2, and the distance between the 1 and 3 is 6. That's why we are taking the minimum distance as the maximum measure of similarity. Now say if it would have been like this, the 1 and 2 would have been 6 and 1 and 3 would have been 3, then we would have connected 1 and 3. So it is just for the sake of convenience, like the matrix is designed like this, so that when we do it graphical representation and do the calculation, it's much simpler to follow. So we will not go by consecutive nodes, because in our picture we have the 1, 2, 3, 4, 5 nodes, but in graph there is no consecutive nodes, right? Because there is no one to say that this is 1, 2, 3, 4, 5. So we will purely go by the similarity between the nodes or between the clusters. So was I able to answer your
Yes,
question?
ma'am. Yes, ma'am. Got it.
Oh, okay. Okay, so no question till now, because then I will go to the next set of algorithm, which is called this fractal clustering.
Excuse me, ma'am.
Yes.
I
Yes.
have a doubt in updation of matrix. Like, uh, why does 1, comma 2 and 3 have 3 as value, and why not 6?
Sorry,
In second matrix,
this
uh,
right? This one comma two or three?
3. Yes,
Yes,
ma'am.
yes, yes. Okay, okay. So, so what is the minimum distance between the cluster 1, 2, and 3? Yeah, see, this one. So it will not have 6 because 3 is the minimum. So are you like, is there any confusion at this stage?
Ma'am, but while defining single link, we took the maximum.
Yes, yeah. So that was the confusion that I also initially did. So while define the single link, we take the closest pair. Closest pair in this case. So yes, can everyone your mic, please? Can please mute your microphone? Yeah. So the closest pairs means the pairs which have the minimum distance. So actually these age weights, do not think them as the weights, because weight means like they are more similar to each other. These are the distance between the the ages. So basically this matrix says the distance between 3 and 1 is 6, and the distance between 3 and 2 is 3. So just like take, like, from Kharagpur, from IIT Kharagpur, Golbazar is say say like 5 kilometers, and the rail station is 4 kilometers, and the India is 10 kilometers. So when I make a graph from IIT Kharagpur as the node, and Golbazar as the vertices, rail station as the vertices, and India as one of the vertices, so I will assign like 5, 4, 10. So these age values are actually the distance. So in the single link approach, as we are taking the closest pair, we will take the mean value. Now, if we would have gone for the complete link approach, where we were taking the farthest pair, we would have gone for the max value. So then the D12, 3 would have been 6.
Okay, got it.
Okay. Okay.
Yes.
Oh, okay. Okay. So, any more question? Okay. So now let us move to this fractal clustering, which is again another type of clustering on the weighted graphs. So was K-means clustering discussed in the class? Yes, no? Anyone was K-means discussed in the previous classes?
No, ma'am.
No, right? Okay. So just to give a context, K-means is one type of unsupervised learning clustering approach, which is also very commonly used on discrete data sets mm, to come up with, like, again with the same objective, to group the instances in the data sets in the different clusters. So now, um, why spectral clustering on the graph, and why not going for the k-means clustering on the graph? So as you can see the output, that on the same data set, these are the output. The left hand side, it shows the output from the k-means clustering. So again, here we have done two clusters, and in the right hand side we have this spectral clustering. Again, here we have the two circles, two clusters. But as you can see, the type of cluster learned are very different in the spectral clustering than in the k-means clustering, right? So for graphs, actually these type of clusterings are desirable to identify the community or the clusters or the giant connected part of the graphs. So that's why we will go for the spectral clustering in the graph. Okay. So there are these are some examples of the spectral clustering on the different data set. So this is on the NIPS data set. So as you can see, in the k-means clustering, it is kind of like, as yesterday we were seeing the pictures of the different groups when we were discussing the k nearest neighbor algorithm. So these are kind of, on the geometrically, because all these are dependent, all these are calculated based on the both the Euclidean distance measured generally when we apply it on the data sets. So these are geometrically making them into, like different adjacent groups or different adjacent clusters. Where if you see in this spectral clustering, it is basically learning the also the shape of the cluster. So this is very important in graphs, because so in graphs it is not that geometrically one group will be adjacent to another group and contiguous like that, right? So different connected parts of the graph may look very different than each other. Okay. So this is an example of the 8 cluster. So NIPS, I believe, I am not sure about it. This NIPS is the actually the conference, the neural information processing, which is now called the newer IPS, and the type of the, like, the different of the authorship network on the NIPS. This is the example of 3 clusters. This is, again, see, this is 2 clusters, but as you can see, based on the structure of the connected component, this is how the 2 clusters are learned. So this is an example of how 4 different connected parts can be grouped into cluster, and these are again 3 cluster and 2 cluster. So all this does not make any sense unless we know what spectral clustering is. So in this spectral clustering, what we will do, we will group points based on the links in the graph. And how will we do it? Okay, so have was Gaussian model discussed in the class? Can anyone tell me?
No, ma'am.
Okay, okay. Oh, okay. So in this case, just let me go back a moment. So in spectral clustering, we will now use probability also to define the similarity between two nodes or two sets of nodes in a graph. So my idea is that now we will group points based on the links on the graph, and based on the links means not the distances like we have seen in the hack, but also the importance of the link, the some kind of similarity between them. So generally, when we want to create a graph from the n-dimensional data, so we use something called a Gaussian kernel. So I think you have heard the term Gaussian, if not like this, but you have heard the normal probability distribution, right? So the normal distribution or the uniform distribution.
Yes, ma'am.
Yeah, so it had the shape of the inverted bell curve, if you remember. Yes, the inverted bell, right? So Gaussian distribution also look very similar to that. So how do I compute similarity between the two objects I and j? So the weight between two objects or two node ij is the exponential of the distance between the xi and xj by the sigma square. So this is the variance, and xi and xj, if I am not mistaken, this is the probability values associated with xi and xj. Okay, so just think it at this point. Just keep it in mind as an equation of the similarity measure between the two sets of object I and j. We will come back to this equation. Even if I forget, please remember, please remind me that we will talk about the Gaussian kernel when we discuss the Gaussian models, okay, in the next classes. So there can be two possible types of graphs. So in any graphs, there can be two possible types of graphs that we can generate. One is the fully connected graphs, that independent of the similarity values between two nodes. They may be very distant from the one another, but we will still connect every two nodes in a graph, and we will assign the similarity values accordingly. So then we will come up with a fully connected graphs, which I have said that means that every two nodes in a graph is connected. Or we can connect only k nearest neighbors. That means again taking idea from our k nearest neighbor algorithm, just we have learned just yesterday. So we can compute the similarity between two nodes, and only we connect the for a node its k nearest node to this particular node. Okay, so that's how there are two possible types of graphs that we can come up with. So these are used in the things like the image segmentation, like to identify like the boundary detections. So now why we do not use minimum cut in the spectral clustering? See, say if we have a node representation, like why we are not using minimum cuts and why we are using this spectral clustering. If this is my graph representation, where will my mean cut algorithm lead me to come up with two sets of graphs where, or two groups, two subgraphs where we have the minimum number of edges between them. So my mean cut algorithm will give some cut from here or here, right? Because see, all these parts are, if we take the proximities, they are more connected to each other or have lesser distances among them. But we can see from the picture that instead of these two mean cut, this is a better cut. But we cannot learn this from the mean cut algorithm. That's why we are going from for a different approach, the spectral clustering. Okay. So, acha. So we will do the whole graph part after. Okay. Okay. So basically with spectral clustering, we are doing graph partitioning. Acha, if at any point, if you feel this is becoming a little overwhelming, please let me know, because right now we will look into the different graph related terminologies. That say we have a set of data points. So based on similarities, we we uh, this, like we make a graph on this set of data points. And so as you can see, this is this bold liner, basically this bold line based on their similarity or closeness or distance, however you define it. So that's why these metrics look like this. So this is a completely connected graph, and on the completely connected graph, our idea is to actually learn these three sets of partitions so that the matrix looks something like this. Okay, we have now three distinct sets of graph, three subgraphs, and we have partitioned the graphs. From the fully connected graphs, we have partitioned the graphs. So this is my data. Based on similarity, we come up with the fully connected graph and the adjacency matrix. And based on this adjacency matrix, we come up with a graph partition. Okay. Now, how do we do that? For that, first let us look into some terminologies related to graph. So, in graph, one of the important term is the degree of the node. So, what does degree of the node means? Basically, if it is an unweighted graph, it is simply how many number of connections a node has. That is the degree of a node. If it is a weighted graph, say then the degree of a node di is equal to the sum of the weight of each of the edges connected to di. Okay, so it is sum of wij where the edge ij is present. So if we are taking a fully connected graph, then this will be the weight with all the other edges, and this will be my degree of the graph. Okay, so it is a discrete value. And in case of the directed graphs, we have two concepts, both the in degree and out degree. So as the name suggests, the in degree means the number of incoming connection to a node, and the out degree means the number of outgoing connection from the node. Now if we assign the weight, again we will follow the same idea. Okay, so this is my degree of the graph. So basically it says how important a node is based on its degrees. And then a volume of a set in a graph. So how do I define a set in a graph? Is basically say if this is my set A with these nodes, these yellow color nodes. So the volume of the set A will be sum of the degrees of all the nodes present in the graph A. So what are the sum of the degrees? All these red lines, the weight of all these red lines. So this will be my volume of a set. Okay, this is again a discrete value. So any question till now? Okay. Okay, so do you want a 5 minutes break?
Yes.
Yes. Okay. Take 5 minutes because uh, we only have like some 40 minutes left in the class. Okay.
Hello, ma'am.
Yes. Yes.
Ma'am, you haven't uploaded slides. Can you please
Yes,
upload them?
I will do it. I will do it. Okay, so let us start. Is everyone back? Is someone back?
Yes, ma'am.
Okay, thank you. Can you see my screen?
Yes, ma'am.
Okay. So we discussed the degree of nodes in a graph and the volume of a set in a graph, in a weighted graph. So now we will look into the graph cut algorithm which to come up with partition within a graph. So now let us start with, say we consider a partition is there in a graph into two parts, A and B. So there are the vertices 1, 2, 3 in the partition A and 4, 5, 6 in the partition B. And these are the weights of the edges in between the two nodes. So cut A and B is defined sum of the weights of the set of edges that connect the two graphs. So that means if we have say like two graphs or two subgraphs like this, so the cut between A and B will be defined as sum of those two edges which are across the two subgroups or across the two parts. That means these edge 1 and 5 and 3 and 4 because these two edges are connecting the parts A and B and not all these other yellow color edges. So what is the sum of weight of the two edges? 0.1 plus 0.3 is equal to 0.3. And again, similar to the mean cut algorithm on the unweighted graph, here also our intuitive goal is to find the partition that minimizes the cut. That means minimizes the cut means for which the cut of A, B for the type of partition will be the minimum or will be the least. And how so and how can we come up with the normalized cut? So the connectivity in this case, we are only taking the connectivity between the two groups, A and B. But normalized means that we are normalizing the value with something. So how can we normalize a sum of set of weight values? So we can normalize it by the volume of the partitions because volume represents the total weight within a particular part. So we will consider the connectivity between the two groups relative to the volume of the each groups. So normalized cut or N cut of A, B is equivalent to cut between AB by volume of A plus cut value between A and B by volume of B. So now basically these cut values are same, right? Cut A, B is same in both the cases, correct? So what only remains is the volume of A and the volume of B. So if I take the cut AB as common, so it will become on top volume A plus volume B by volume A into volume B. Now when this value is the minimum, when the volume A is equals to volume B, right? When the two value becomes equal, this will be minimum. I am correct. So this will encourage a balanced cut. If we also take the volume into account apart from the cut value. So that's why it is called the normalized cut. Understood till now the graph cut and the normalized cut? Please let me know if you have any question.
Ma'am, can you give us small examples for normalized graph?
Okay. So now let's go back to this example. So what is the volume of A? The volume of the partition A, and I encourage all of you to what you would have done in a regular classroom is please take a pen and paper, and whenever you see these kind of derivations, please also write them down. Even if you are writing it while seeing the slide, but then also writing will help retain it better. For that, if you need some time, let me know. I will stop and you can write. But it may look very trivial when we see. That also happens with us also. But when you will write, you will get the queries. So can anyone tell me that what will be the volume of this part A? From
25, I guess.
yes.
2.5.
2.88.
5.
How much is 16?
I mean, it be 2.2.
2.2. This is 2.2, and this is
2.3.
2.3. And what will be the card value? Actually, yeah, someone said 2.5. That is right. Why? Thank you. I also.
Ma'am, it is
So
the
we
sum
consider
of
all
all
dates.
degrees. No?
Yes. All degrees. So
So
just
in
limit
that case,
picture.
there will be like for the 1 it will be 0.8 plus 0.6, and then for 2 it will be 0.8 plus 0.8. So it will be 2 into the sum of all edges.
No. It will be 0.8 plus 0.8 plus 0.6, and yes, it will be 2 into the sum of all edges. That's correct. Yes, because we are yes. If we are taking the degrees, yes, it will be the 2 into the sum of these two, but it will be just one time these two, because we are not considering 4 and 5 in the part A. So let us go back to this. So the degree of DI. So what is the degree of the node 1? 0.8 plus 0.6 plus 0.1. The degree of the node 2 is 0.8 plus 0.8. The degree of the node 3 is 0.6 plus 0.6 0.2. And then the volume of a set is the degree of all the nodes, the sum of the degrees of all the nodes belonging to the set. So it will be basically 2 into 0.8 plus 0.8 plus 0.6 plus 0.1 plus 0.2. Am I correct?
Yes, ma'am.
Anyone have any doubt? Please feel free to ask.
Ma'am, while calculating D, we do not consider whether it's an incoming edge or an outgoing edge. We
No.
just add all bits.
Yes, because this is an undirected graph, so we do not consider that. Like, so the direction is not present. It is not that we do not consider. So this graph is undirected. So all the edges are bidirectional. We can take.
Ma'am, so like if it was directed, then we would consider only like which kind of edge?
Actually, what happens if it becomes the directed graph, then there are the concepts of, as I said, the in degree and the out degree, and then all the calculations, they will be specified based on whether they are done on the in degrees or on the out degrees. Okay, so then like my graph card, it will be also dependent on what kind of degree or type of edge connections I am considering. And actually the connectivity will also depend on the edge direction. So it will be different than how we are approaching it now. Okay, so does everyone come up with the volume of part A? Can anyone give me the answer, please?
4.7.
4.7.
4.7, correct. And the volume of card B?
4.9.
4.9.
4.9, correct. So then if we so what will be the value of the normalized card between A and B? It will be 0.3 by 4.7 plus 0.3 by 4.9. So basically if we take the 0.3 common, so this will become like this: 4.7 plus 4.9 by 4.7 into 4.9. Now when this value is minimized, when these two are equal, when volume A is equals to volume B, then we will come up with like something like volume A square or volume B square. So that will be the minimum value, right? Because in every other value, the one value will be greater than the other. So the minimum value is that when these two are equal. So this encourages, if we attempt to minimize this encourages a more balanced card. Is it clear till now? Do you need some time to write it down, process it?
Ma'am, could you explain again how volume is calculated?
Yes, from this formula. So a volume of a set or a part on a graph is calculated as sum of all the degrees of the nodes present in the set. So now my degree of a node is this set of the weight, this sum of the weights of all the edges in a graph. So if I take this yellow colored mark nodes are say from the set A, then till this red ones we have the edges. So sum of all the weights are like 2 times this internal weight will be the volume of a set. So basically all the nodes which are present in the particular part, the sum of their degree is the volume of the part. Okay. So it's clear. Is it clear?
So is it like all the edges which are connected to the vertices?
Yes, yes. All the edges which are connected to the vertices belonging to the particular set. Okay.
Okay.
These all the yellow colored vertices are from the set A. So we are considering all the edges from these vertices. So, okay. It's clear.
Ma'am, could you show the example once?
This one?
So for set A, it should be 0.8 plus 0.8 plus 0.6, that is 2.2, plus 0.3, it should be 2.5.
Yes.
The
So why
volume.
did we 0.7? See, in the volume definition, this DI is the degree of the node. Okay. So now for each node, we are calculating its the edges. So basically, then if we are taking like for say like take this edge. Take this edge. Okay. When we calculate its DI, we are taking this node, this edge, this edge, this edge, this edge. Correct. Now let's take this node. When we are calculating di of this node, we are again taking this edge, right? So all this edge in this part, this connected component is actually getting calculated twice if we are adding up all those DIs, because DI is itself the sum of all the edge weights. So that's why we have taken this 0.8 plus 0.8 plus 0.6 to 2 times, because what is the degree of the node 1? It is 0.8 plus 0.6 plus 0.1, correct? The degree of node 2 is 0.8 plus 0.8. The degree of node 6 is 0.6 plus 0.8 plus 0.2. Am I correct? So then if I add up all the degrees, so basically I am calculating these three the edges 2 times each. Am I correct?
Yes, ma'am, got it.
Yeah. That's why it became 4.7 and 4.9. So is it all clear till now?
Yes, ma'am. Yes, ma'am.
Okay. Okay, then I think we are almost at 10, so I will stop here. If there is no more question, we will complete it in the next class.
Can you tell us about the offline classes, like and the exams, or what is the status with that?
Yes, actually, so it is Shreyas again, and just after yesterday's class, I saw the mail actually which you all have received regarding the offline the end semester the examination. But as I said, like officially for to us, we have not received any notification till now. So it may or may not happen, but I cannot really comment on it because my information source is the same as yours. And the offline classes, actually, there was initially a notification that for second and third years, whoever are in campus, the offline classes can start from 10th March. But actually, frankly, we are also in a fix because we do not know how many are in the campus and how many will come to the offline class, and then also the classroom allocations, because this semester the classes were going online, we really did not went for the classroom allocations. So I think Adday sir has started a survey in the teams that who all wants to attend the offline classes. Yes, no? So do you want to attend offline classes? Like,
No, I was asking because I am at my home, so that's why I wanted to know what is.
no, see,
Up.
even if we take offline classes, it will be in a hybrid mode this semester, because till 31st March people are coming, right? But again, as I said, there are some logistic challenges, because unless we know how many we are actually expecting, we need to raise also the classroom request, and also basically what we are thinking that if maybe this semester we can continue in the online mode, and if possible we may meet at the end for one or two classes offline. And from the next semester we'll resume the offline classes as it is.
Okay, ma'am. Thank you.
Okay, is it fine? Okay, so any other question or query?